Are you preparing for a senior-level Java interview? In this video, we dive deep into advanced object-oriented programming (OOP) concepts in Java tailored for professionals with 11+ years of experience. Whether you're targeting roles like senior Java developer, technical architect, or engineering manager, these expert-level OOP interview questions and answers will help you refine your knowledge and prepare with confidence. 1. What are the core principles of object-oriented programming in Java? Java is based on 4 fundamental OOP principles: encapsulation, inheritance, polymorphism, and abstraction. Encapsulation is the practice of bundling data, variables, and behavior methods that operate on the data into a single unit, typically a class. It hides the internal state and requires all interaction to be performed through an object's methods. This protects the integrity of the object's data and promotes maintainability and modularity. Inheritance allows one class to inherit the properties and behavior of another class, promoting code reuse. This creates a parent-child relationship, enabling hierarchical classifications and polymorphic behavior. Polymorphism allows one interface to be used for a general class of actions. The most common types are compile-time method overloading and runtime method overriding polymorphism. It simplifies code and improves extensibility by allowing one implementation to be replaced with another dynamically. Abstraction involves hiding complex implementation details and exposing only the essential features. It allows developers to focus on what an object does instead of how it does it. In Java, abstraction is achieved through abstract classes and interfaces. 2. How is abstraction achieved in Java, and when would you use it? Abstraction in Java is achieved through the use of abstract classes and interfaces. An abstract class can provide a common base with shared code, while interfaces define a contract that implementing classes must fulfill. You'd use abstraction to define layers of responsibility, promote loose coupling, and allow code to evolve without impacting higher-level logic. For example, in a service-oriented architecture, interfaces allow different services to change or evolve independently provided they maintain the same contract. 3. What is the difference between abstract classes and interfaces in Java, especially after Java 8? Originally, interfaces could only define method signatures, while abstract classes could provide method implementations and constructors. However, Java 8 introduced default and static methods in interfaces, narrowing the gap. Despite this, abstract classes are still preferred when there is shared code or state. Interfaces are best used for defining capabilities or roles that a class can perform, especially when multiple unrelated classes need to implement the same behavior. The key difference lies in the intention. Abstract classes are used for hierarchical relationships, while interfaces represent contracts that can be implemented across unrelated classes. 4. How do you apply polymorphism in real-world Java applications? In real-world applications, polymorphism is central to achieving flexibility and scalability. It allows objects to be treated based on their common interfaces rather than their specific types. For instance, in a payment processing system, different payment methods like credit card, PayPal, or bank transfer might implement the same interface. At runtime, the appropriate implementation is selected based on user input or configuration without changing the code that uses these objects. This design pattern decouples the logic from specific implementations, enabling plug-and-play extensibility and adherence to the open/closed principle of solid design. 5. Can private or static methods be overridden in Java? Private methods are not visible to child classes, hence they cannot be overridden. Static methods belong to the class, not the instance, and their resolution is done at compile time. Therefore, if a subclass defines a static method with the same signature, it hides the method in the superclass, it does not override it. Understanding this is critical to avoiding unintended behavior in polymorphic hierarchies and static utility classes. 6. What is the purpose of access modifiers in object-oriented design? Access modifiers define the visibility of class members and are fundamental to encapsulation. By restricting access to internal components of a class, developers can prevent unintended interference, ensure integrity, and enforce boundaries between different components or modules of the system. This also supports the principle of least privilege and information hiding, which enhances security, testability, and maintainability. 7. Explain composition versus inheritance and when you prefer one over the other. Composition and inheritance are both used for code reuse, but composition is generally preferred in modern design due to its flexibility. Inheritance creates a tight coupling between parent and child classes. Changes in the superclass can have ripple effects on all subclasses. Composition, on the other hand, involves constructing classes from other classes by including instances of them, which leads to loosely coupled designs. Use inheritance when there is a clear is-a relationship. Prefer composition when the relationship is has-a, or when different behaviors need to be combined dynamically. 8. What are some OOP-based design patterns you've used in your projects? Design patterns are proven solutions to common design problems and are deeply rooted in OOP principles. The factory pattern promotes object creation based on abstract types, aiding in polymorphism. The strategy pattern allows swapping of algorithms dynamically using composition. The decorator pattern supports dynamic addition of behavior to objects without altering the base class. The observer pattern helps implement publish/subscribe systems in a decoupled manner. The singleton pattern ensures that a class has only one instance and provides a global point of access. These patterns increase code clarity, reusability, and testability. 9. What is the difference between aggregation and composition in object-oriented modeling? Both are forms of association between objects. Aggregation represents a weak relationship where the child can exist independently of the parent, such as a university and its students. Composition is a stronger form where the child cannot exist without the parent, like a house and its rooms. This distinction matters when modeling domain entities, especially for persistence and life cycle management. 10. Explain the SOLID principles and how they relate to OOP. SOLID is an acronym for 5 principles that guide robust object-oriented design. Single responsibility principle: each class should have only one reason to change, promoting focused functionality. Open/closed principle: classes should be open for extension but closed for modification, encouraging polymorphic behavior. Liskov substitution principle: subtypes must be substitutable for their base types without altering the correctness of the program. Interface segregation principle: clients should not be forced to depend on methods they don't use, leading to more granular and role-specific interfaces. Dependency inversion principle: high-level modules should not depend on low-level modules, both should depend on abstractions, promoting loose coupling. Applying these principles leads to systems that are easier to understand, test, extend, and maintain. 11. How do you prevent or control inheritance in Java? To control inheritance, you can mark a class as final, which prevents other classes from extending it. This is useful when you want to ensure the behavior of a class remains unchanged and is particularly common in utility or security-critical classes. Another approach is to favor composition or provide package private constructors to restrict subclassing to specific packages. 12. What are common mistakes developers make when using OOP in large-scale applications? Overengineering with inheritance: trying to create generic hierarchies too early can lead to rigid and brittle designs. Violation of encapsulation: making fields public or overexposing internal details leads to tight coupling and less maintainable code. Ignoring design principles: neglecting principles like SRP and OCP results in large, monolithic classes that are hard to modify. Not using interfaces effectively: coupling to concrete classes limits flexibility and testability. Improper use of static methods: excessive reliance on statics breaks polymorphism and makes unit testing harder.